If you can see this right now and you can hear my voice as well, that implies that you decided to click on the video regardless of the warning. Anyways, you might want to reduce the brightness of your phone to prevent any storage that touch. So today is the last day of 50 days of tutelage, and we're going to be talking about radioactivity. Radioactivity. When you hear radioactivity, one of the things that come to mind is that it's it is the emission of harmful substances. But beyond that, the concept of radioactivity can be very, 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 very important, and they can be very, very useful, especially in modern physics. So, what is radioactivity? Radioactivity is the spontaneous and random disintegration of an unstable nucleus with the emission of radiations. Like this radiation can be particle, they can be in form of energy, and when they emit this, they form more stable nucleus. In fact, if an emission takes place and then during the emission you emit another unstable nucleus, so that means that another emission can also take place. So emission stops when you have what? When you have reached all stable nucleus altogether. So radioactivity is basically, so you have a random nucleus here, and then this nucleus it disintegrates over time and it gives birth to other nucleus. So we call them nuclei rather, other nuclei rather. And then this is the parent nuclei, by the way, parent nucleus, and these are the daughter nuclei. And so what you notice here is that if any of this is also like unstable, then the whole process continues as well. That's basically what radioactivity is all about. Now, another feature we notice about these radioactive substances, that is radioactive atoms, is that the ratio of their neutron and proton. In the earlier classes, I already taught you about atomic structure. So where you have proton the same as atomic number, and then neutron is the difference between the mass number and the proton number. So when you look at the ratio of proton to neutron of radioactive substances, that is those unstable substances, it's always very unstable as well. That's one of the features, one of the properties that we see with radioactive substances. So the key thing is that we have three major types of radiation, three major types of emission when radioactivity is occurring. And these three guys, we have two particles and we have one of them as a ray. So we have the alpha particles, we have the beta, we have the beta particles, and then we have the gamma. We have the gamma ray. We have the gamma ray. So these are the three major particles that we have. We have two particles and we have what? We have a single ray. So these three guys are the major emission that we experience during radioactivity. And these guys, they have their different properties. So I'm going to give you a few of them, a couple of them. Alpha particles is analogous to helium atom actually. So helium atom, helium atom has two protons and the mass number is 4. So that means it also has two neutrons as well. And what we notice about this guy is that it has a charge of +2. It has a charge of +2. Then it is very, very slow. It is very, very slow. Due to this being very, very slow, it has very low penetrating power. It has very, very low penetrating power. It can easily be stopped by paper or just the skin. But in terms of ionizing power, it has very strong ionizing power as well. So these are the major properties of the alpha particles. So the next particle is the beta particle. Beta particle is sort of analogous to electrons, and we know that electrons, they have a charge of -1 and they move very fast actually, up to like they move as fast as up to 99% the speed of light. So they have moderate penetrating power. They can be stopped by, let's say, 5 millimeters of aluminum. So if you bombard them into a fine sheet of aluminum, like 5 millimeters of aluminum sheet, I mean 5 millimeters, so that they can be stopped by that. So they have moderate penetrating power. So they have a charge of -1. And in terms of their mass is also negligible. Unlike helium, the mass is still like very significant, but for electrons, their mass is actually very, very negligible. So take note, it has a charge of -1. It has moderate penetrating power. And in terms of ionizing power as well, it is also moderate as well. That is for radioactive, so for beta particles. And beta particles, they are greatly affected by photographic plate. So they are strongly affected by photographic plate. For helium, they are weakly affected by photographic plate. And if they enter a field, for beta particles, they are deflected strongly towards positive plate in a field. So when you have the positive plate, the beta particles are going to be deflected towards positive plate. As you can see, they are negatively charged. So automatically, from law of attraction, negative charge will be attracted towards to positive charge. So that is that. And for um, alpha particles, it's positively charged, so it will be strongly, maybe not strongly, it will be slightly attracted to the negative pole in any plane. So that's that. You should take note of that. Then the last one is gamma ray. So you can see this one is not a particle. This one is actually a ray. Now, for this ray, it is an electromagnetic wave, so it can be treated as a photon. It will be traveling at the exact speed of light as well. All those electromagnetic waves, they travel at the speed of light. Now, it is neutral. It does not have any charge. Like I said, it is not a particle, it is a ray. It does not have any charge. It does not have any mass. So it has moving exactly at the speed of light. So it has very high penetrating power. It needs something like a thick lead or concrete before you can stop them. So they are very high. That is why in the laboratory, wearing the lab coat that is laced with lead can be one of the ways to prevent yourself from getting harmful emission penetrate through your body. So they have very high penetrating power. But when it comes to ionizing power, they have very, very weak ionizing power, and they are not defected in the field at all. So when they are passing through a field, so if you have a field, you have a positive plate here, you have negative plate here. So what you notice is that from this movement, there is one particle that will go in this direction. I think I should space this properly. So if you have a field, you have a negative pole here, you have a positive pole here. So if you have three particles traveling like this, so one particle will move towards this place, and then one particle will move in this manner, something of that nature, slightly defected, and one particle will just go straight like that. So you can easily tell that this guy is your beta particle. This guy is the beta particle, and then this is the alpha particle, and this is the gamma ray. So that's the way they behave in plane. So and they are also affected. Gamma. I'm back to gamma ray now. Gamma ray, they are affected by photographic plate. They are affected by photographic plate. So that's basically the three different emissions that we have during radioactive emission. Now, we need to look at the nuclear decay. How can we actually like represent this nuclear decay with an actual equation? So for instance, if we have a very, very heavy nucleus, like nucleus of uranium now, so if uranium is being, let's say you have this, the mass number is 238, and then the atomic number is 92. So for alpha particles, we have atomic number of 2 and mass number of 4. For the beta particle, this is what you have. You have 0 here and you have -1 here. And for the gamma ray, there is nothing, there is no mass, there is no atomic number. It's just a ray. So if there is an emission in a situation whereby you have 3 of these being emitted and you have 4 of these being emitted, so what exactly are we going to produce at the end of the day? So you have something of this nature. So you are producing 3 of these. So let's put 2 here, let's put 4 here. Then you are producing 4 of these, -1 beta. Then let's say you are producing just 7 of these. 7 of these. Now, for this 7 of these, it will have no effect in this whole thing. It will have no effect. But for these other guys, they will definitely have effect. So this is what you do. There is another guy that is missing here. Another guy is missing in this spot here, which is actually going to be the more stable nucleus than uranium that was created due to this emission. So to look for that guy, we need to find the atomic number and we need to find the mass number of that guy. So let that guy, let it be X. So the atomic number of that guy is going to be, let's say it is A, and let the mass number be M. So from here, we notice that if we find the sum of M plus, we have 3 of these, so that's 3 times 4, that's 12, plus 4 times 0 is 0. That must be equal to 238. So easily we can solve for M here. M is going to be 238 minus 12. So what's 238 minus 12? 8 minus 2 is 6. And 3 minus 1 is 2. So that's 226. So now we have the mass number. For the atomic number, we do the same thing. So we have A plus, we have 3 times 2, that's going to be 6, plus 4 times negative 1, that's going to be negative 4. And then this has no effect. So everything here is going to be equal to 92. So here we have 6 minus 4, that is 2, plus A equals 92. So obviously A is going to be 90 like that. So from here, this guy is going to be 90 and this guy is going to be 226. Of course, I'm sorry, I don't know which atom is this. So you can easily Google that on your own and find which atom this X is. So that's basically what you notice with this emission. You should always be able to identify and do any form of calculation that you are given in any mode like this. This is how you just equate them and then you solve them simultaneously in this manner. So quickly, let's talk about half-life. Let's talk about half-life. So before I give any textbook definition, we're going to break down the word into two. We have the word half. So we have half and we have life. So life is basically time. It's talking about time. So time. And then half, of course, when you split something into two. So whenever you have a certain nucleus, and then this nucleus, it breaks down into half of itself. Then the time it takes for it to turn from this original nucleus to half of itself, that time is what we call half-life. By the way, this guy can also break down and turn into half of itself. The time it will also take is also called its half-life. So what is going on here is that a substance can decay up to becoming half of itself. So the time it will take for this to happen is what is called half-life. So let me give you a textbook definition now. So half-life of a radioactive substance is simply the time taken for half of the original number of unstable nuclei of a radioactive sample to decay. So half-life is always constant for radioisotopes and it is unaffected by temperature, pressure, or chemical state. So I'm going to be doing a little bit of math. So let's say we have the original amount of a substance. Let's call it N naught. So what happens is that if it goes and become N naught over 2, then this one can also go and become N naught over 4. That is, I'm just finding the half of all of these. And it can go and become, so when you find half of these, it will become N naught divided by 16. So what you notice here is that this one happens after 1 half-life, 2 half-lives, 3 half-lives, and it goes on and on like that. But I notice a pattern here. This is like a geometric progression. A geometric progression such that the first term is N naught and the common ratio is 1 over 2. And you know that generally we can represent any term of a geometric progression. We can represent it using AR raised to power N minus 1, where N is a particular term that we are dealing with. So in this case now, if we want to do such representation, so to represent any term that we get to here, we can say A is N naught multiplied by R, which is 1 over 2, then raised to power N minus 1. So let this be the value of any N that we want to get to, that is any term that we want to get to. But since this whole thing, I want to customize it using the number of half-life that has been experienced. So notice that for every term here, this is like the second term. How many half-life have I experienced? Just 1 half-life. This is the third term here. How many half-life have I experienced? 2 half-lives. This is the third term here, a fourth term. How many half-life have I experienced? 3 times. So that implies that the number of half-life that you have experienced is like one value less than the number of times that you are actually. So instead of using N minus 1 here, we will now tailor this thing using the number of half-lives that has been undergone. So let this represent the half-life. T half, let's it represent the half-life. So that implies that n now becomes n naught multiplied by 1 over 2. Then we now say number of half-life now. So we're not interested in the term again. We will not, n will not represent the term now. N will represent the number of half-life. So the number of half-life, that will be n 1, 2, 3 multiplied by what the half-life is itself, which is t. So we can have this is n multiplied by what? T half. N multiplied by T half. So this is going to be the general representation. With this now, you can find any form of thing that you're looking for. For instance, if let's say a certain guy started with 32, and then you want to look for what it will become after it has on. Let's say the half-life is also 2 years. Every 2 years, the half-life is every 2 years. So let's say now you want to see how much this thing would have become after 10 years. So after 10 years, how much would it have become? So it is very easy here. Instead of this nt half, you can just say n equals n naught is 32, then 1 over 2, then you raise that to power 10. But what is going on here is that you have actually been able to say that this guy is 10, which is 5 half-lives. So 2 years, 2 years, 2 years, 2 years, 2, 1, 2, 3, 4, 5. So these are 5 half-lives altogether. So this 10 is actually the same thing as 5 times 2. 5 times 2. So this n shows the number of half-lives, and then this T half shows the half-life itself. But this guy can also be generally represented as n equals n naught multiplied by 1 over 2 raised to power t. So what is t now? T is simply n multiplied by T half, where t is the total time taken for the decay to happen altogether. Another common expression is the expression n equals, let me write that properly, n equals n naught multiplied by e raised to power negative lambda t. So in this case, lambda is regarded to as what we call the decay constant. Lambda a is the decay constant. And how do we find the decay constant? So we just pick an arbitrary value. So let's say, for instance, we want to look for the time that it will take for this guy to become half of itself. That means that we're looking for when n equals n naught divided by 2. So if you substitute that into this expression, you have n naught over 2 equals n naught multiplied by e to the negative lambda t. From here, n naught can cancel out, and then so what you notice here is that we have 1 over 2 equals e to the negative lambda t. And from here, to solve for t now, this t is going to be t half actually, because what I did was that I used when n equals n over 2, n naught over 2, meaning that I'm looking for the time that it takes for this guy to become half of n naught. So therefore, the time here will actually be the half-life based on what I've defined earlier. So in that situation, I will be able to get the relationship between the decay constant lambda and the half-life. I can just take the natural logarithm of both sides. So ln of this is this. So with this, that implies that I have ln of 1 over 2 equals negative lambda multiplied by T half. So what we know is that ln E equals 1. So that is just logarithm. So having this now, I can then see that this is the same thing as ln 2 raised to power negative 1. So equals negative lambda times T half. So the negative sign can come to the other side. So you have negative ln 2 equals lambda times T half. And the negative sign is going to cancel out from there. So we have the negative sign cancelling out. Yes, cancelling out here. So therefore, the product of lambda, which is the decay constant, and half-life is going to be ln 2. So this is a general expression actually. The product of decay constant and half-life is going to always give ln 2. It's going to always give ln 2. So that's basically what this is about. So you can always use it to calculate your half-life and all of those things. And many other things as well. You can be asked to find how much substance is left or how much substance has decayed. If you're looking for how much substance is left, you can just use this expression I've given here, using the number of half-life that it has undergone. So if you know the half-life, just calculate the number of half-life it has undergone, and then you can put it into this expression that I've explained earlier. Then you know how many things is left. So if you know what is left, then you can know what has been removed so far. For instance, if you have n naught over 16 left, that means that what will be left will be n minus, sorry, what has decayed will be n minus n naught over 16, and that will be 15 n naught over 16. So that's basically how you do such calculation. Now, to conclude this class, I will talk about these two things: nuclear fission and nuclear fusion. Nuclear fission and nuclear fusion. So, if we have a substance, like if we have like different nuclei, or we have a single nuclei being separated, and we have different nuclei coming together to join to become one, then we are talking about the concept of nuclear fusion and nuclear fission. So, for nuclear fission, nuclear fission. So what we have here is the splitting of heavy unstable nucleus into lighter nuclei. So when you have a very heavy guy splitting into lighter ones, then we have what we call nuclear fission. So the opposite is where we have nuclear fusion. For something to fuse together, I wrote fusino. For something to fuse together, nuclear fusion. In this case, you have the combining of nuclei together. They combine and they form heavier nucleus. So in the case you have this N1, N2, they join together and they form heavier nucleus. And that is what nuclear fusion is about. So this is the basic thing about radioactivity. Of course, like there's always other thing, but for this video, I'm going to limit it to this concept only. Make sure you are subscribed to the channel and make sure you like the video as well, so you get to see more of my videos that explain some other concepts that I probably have not covered in this video. I'll see you in the next one.